Right now, in a laboratory in Mountain View, California, there is a metal cylinder hanging from the ceiling by superconducting wires. The temperature inside that cylinder is 15 millikelvin. That is 15 thousandths of a degree above absolute zero. It is colder than the surface of Pluto. It is colder than the void between the stars. It is colder than anything the natural universe produces at any meaningful scale. And inside that cylinder, at that temperature, something is happening that our best physical theory cannot fully explain. The machine is called a quantum processor. The thing it is doing is called superposition, and what that word means, in the most precise physical sense, is that an object inside that machine is simultaneously in two contradictory states at once. Not probably, not approximately. Actually. Right now. And it has been doing this since the moment the calculation started. In 2019, a processor running at 15 millikelvin completed a specific calculation in 200 seconds. The world's fastest classical supercomputer would have needed 10,000 years. Not 10,000 hours, 10,000 years. But the part that disturbed physicists was not the speed. It was what the machine had to be doing physically in order to run at all. It had to be in superposition. Genuine, physical, irremovable superposition. Genuine, physical, irremovable superposition. And if that is true, it means the world, at the level where the physics actually lives, is not what you think it is. By the end of tonight, you will understand why. You will understand what superposition really means, what it says about reality between observations, and why the physicists who work on this are not being dramatic when they use the word horrifying. They are being precise. If you love science that sits with the hard questions instead of walking past them, take a second to subscribe. This channel is built for nights like this. Now, let's begin. The filing system most people carry about quantum mechanics has a label on the quantum drawer that says something like, "Interesting for physicists, confirmed in experiments, important for technology, but somehow separate from the world I live in." That label is a reasonable response to how quantum mechanics is usually taught. The strangeness is presented as a feature of the very small. The electrons and photons are weird. The table and the coffee cup are not. The weirdness is real but contained. It stays down at the bottom of things and does not reach up into daily life. The containment was always more fragile than it appeared. Every transistor in every classical computer you have ever used is built on quantum mechanics. The conductivity of silicon, the behavior of electrons in semiconductor junctions, the discrete energy levels that make digital logic possible, none of these exist without quantum mechanics being exactly as strange as it is. The classical computer is built on a quantum foundation. It just does not expose that foundation to the computation. The quantum processor, by contrast, brings the foundation to the surface. It operates in the regime where the quantum effects are not the background physics that makes the machine possible. They are the machine. There is a reason physicists don't often say what they're about to say here. It isn't evasion. It is that the question of what quantum computers are doing opens into the measurement problem. And the measurement problem opens into the interpretation problem, and the interpretation problem has no agreed resolution after nearly 100 years of effort by some of the most precise thinkers in the history of science. So the usual approach is to present the results, note the weirdness, and move on before the audience has time to sit with what was just said. Tonight, we are not going to do that. Tonight, we are going to sit with it. Because the results deserve that, and because the question of what reality is between observations is not an idle philosophical question. It is the question that the machines are raising every time they produce a result. What you are about to encounter is not speculation. It is the confirmed experimental physics of the last 100 years, brought into contact with the technology that has been operating commercially for less than a decade. The quantum mechanics is old. The measurement problem is old. The philosophical arguments are old. What is new is the scale. What is new is the fact that the systems demonstrating genuine quantum behavior now contain not one particle, not 10 particles, but hundreds of qubits operating in concert, producing outputs that no classical machine can replicate. This changes the character of the debate. Not its resolution, but its urgency. The question of what is really happening inside a quantum computer is no longer a question you can defer to philosophers. It is a question about what your computer is made of. And the answer is stranger than the question. A classical computer is a machine that does exactly what you tell it to do. It works with bits, each one a switch that is either on or off, 1 or 0, never both. A transistor carries current or it doesn't. A memory cell stores a 1 or a 0. The entire system, from the processor in your phone to the server farms that run the internet, operates on this binary foundation. It is deterministic, readable, and entirely consistent with the world you experience when you flip a light switch or turn a key in a lock. Every piece of information inside a classical computer is either this or that. Nothing is ever both at once. The machine never asks itself what state it is in, because the state is always definite. Definiteness is not a limitation of classical computing. It is the entire point of classical computing. A quantum computer is something structurally different, not faster in the way that a sports car is faster than a family sedan, where the underlying mechanism is the same and one version just does it more efficiently, different in the way that a submarine is different from a bicycle. The device does not use bits, it uses qubits. And a qubit is an object that can exist in a superposition of 0 and 1 simultaneously, not alternating between them at high speed, not switching between them so quickly that it appears simultaneous. Simultaneously, in both states at once, until you measure it. The moment you measure it, it becomes one or the other. Before measurement, it is genuinely both. That word, genuinely, is doing a great deal of work. It means this is not a figure of speech, it is what the physics says is happening. The qubit is a physical object, typically a superconducting loop cooled to 15 millikelvin. That number means 15 thousandths of a degree above absolute zero. The surface of Pluto sits at about 40 Kelvin. The diffuse void between the stars sits at about 3 Kelvin. The interior of a dilution refrigerator, cooling a quantum processor, sits 15 times colder than that. Colder than deep space, colder than anything the natural universe produces at large scales. This extraordinary cold is not an engineering quirk, it is a physics requirement. At those temperatures, quantum effects dominate so completely that a superconducting loop carries current in 2 directions simultaneously. Each qubit is isolated from its environment as completely as the engineers can manage. Quantum processors operate inside nested layers of material that block radio waves, microwaves, magnetic fields, and vibrations, because any of these can carry information about the qubit state to the outside world. And if the outside world gains information about the qubit state, the superposition collapses. The qubit becomes definite. The quantum computation fails, not slows down, fails. The engineering challenge of building a quantum computer is, in large part, the challenge of keeping the quantum system ignorant of its environment for long enough to do something useful. Think about the engineering requirement from the other direction. Classical computers generate heat. They run at room temperature, in office buildings cooled by ordinary air conditioning. You do not need to go below room temperature to keep a classical transistor classical. It is classical on its own. It stays classical because the physics says it must. Now think about what it means that quantum processors require the most extreme artificial cooling conditions ever achieved by human engineering. Every precaution the engineers take is a precaution against the thing that would destroy the superposition. The fact that all those precautions are necessary is proof that the superposition is real enough to be destroyed. You cannot protect something that does not exist. The dilution refrigerator is not the only layer of protection. Outside the refrigerator, the quantum processor is surrounded by a Faraday cage, a room-sized metal enclosure that blocks external electromagnetic interference. The cage is sometimes lined with mu metal, a material with high magnetic permeability that shields against low-frequency magnetic fields. The control electronics that send signals to the qubits are connected through heavily filtered cables that allow the desired microwave pulses through while blocking thermal noise. The floors are floated on air cushions to reduce mechanical vibration. Some facilities operate on nights and weekends when surrounding laboratories are quiet and vibration from foot traffic is minimized. The entire enterprise of quantum computing, from the refrigerators to the cables to the timing electronics, is a sustained engineering campaign to create an environment where the laws of physics operate without the constant intervention of the classical world. And in that environment, Inside that carefully constructed absence of classical information flow, the qubits do something no classical object can do. When Google's Sycamore processor ran its benchmark calculation in October 2019, it used 53 qubits in superposition simultaneously. A classical computer attempting to simulate this must track every possible combination of states those qubits could be in. 2 qubits have 4 combinations, 3 have 8, 10 have 1024, 20 have over a million, 53 have over 9 quadrillion, 9 million billion distinct states. The table required to simulate the Sycamore processor faithfully would require more memory than all the digital storage on Earth combined. The world's most powerful classical supercomputers cannot hold it. They approximate, and the approximation degrades as the system grows. The quantum processor doesn't simulate the quantum system. It is the quantum system. The computation happens because the physical states are genuinely overlapping. The interference between those states produces the correct answer, and removing the superposition makes the computation fail completely. The result is only accessible because the thing is actually happening. And if you accept that the computation works, and it does, you are accepting that superposition is real, physically real, not mathematically convenient. Real in the way that the ground beneath your feet is real. Take a breath here. The machine works. The machine working is the evidence. And what the evidence is evidence of is a physical system existing in genuinely contradictory states simultaneously. A loop of superconducting metals smaller than a grain of rice, carrying current in 2 directions at once. Before you measure it, before you ask it to choose, it is both. Not probably both. Not approximately both. Not approximately both. Both. And if that is true of the qubit, what is the world like for that object while it is in that state? What does it mean for something to exist as 2 contradictory things at the same moment? The physics has the mathematics to describe it precisely. What it does not have, after nearly a century of effort, is an agreed-upon answer to what the mathematics is pointing at. Think about this from the perspective of what classical physics says should be impossible. Classical physics says that every object at every moment has a definite state, a definite position, a definite velocity, a definite energy. These are not approximations. They are the foundation of every intuition you have about how the world works. When you roll a ball across a table, the ball is somewhere specific at every moment. When you flip a coin, the coin is on one face or the other. The state is always definite, always one thing. This is not just common sense. It is the entire structure of classical mechanics, the theory that was spectacularly successful for 3 centuries before quantum mechanics arrived. A qubit violates this at the most basic level. It is in a superposition that has no classical equivalent, a physical state that is genuinely neither 0 nor 1 until measurement forces it to choose. This is not because the qubit is small. Smallness alone does not produce quantum behavior. It is because the qubit is isolated from its environment deep enough and cooled enough that quantum effects dominate and classical effects become negligible. It is an object in a genuinely different physical regime, one where the rules of classical mechanics simply do not apply. The 53 qubits in the Sycamore processor were not 53 separate objects each in its own superposition. They were 53 objects in a single entangled superposition, a joint quantum state that cannot be described by 53 separate wave functions, but only by a single wave function spanning all 53 objects simultaneously. The 53 entangled qubits together constitute a quantum system with a state space of 9 quadrillion dimensions. No classical system of 53 objects has a state space anywhere near that size. The exponential scaling of entangled quantum state spaces is precisely what makes quantum computers powerful, and it is precisely what requires superposition to be real. Consider the block sphere more carefully, because it is where the strangeness becomes concrete. A classical bit can be in exactly 2 states, North Pole or South Pole, 1 or 0. There is no intermediate state. The bit either is or it is not. A qubit can be at any point on the surface of the sphere. The North Pole and South Pole are the measurement outcomes, 0 and 1. But between those poles, wrapping around the entire surface, are the superpositions. A qubit at the equator is in an equal superposition of 0 and 1, with no bias toward either outcome. Move it slightly north, and it becomes slightly more likely to read as 1. Move it to the exact north pole, and it is in the definite 1 state. Every point on the sphere is a physically distinct quantum state. Every one of those states is physically real. The qubit is not choosing between them. It is at a specific point on the sphere, and that point encodes a genuine physical reality that has no classical equivalent. Quantum gates are rotations on this sphere. A Hadamard gate takes a qubit from the North Pole, the definite 0 state, to the equator, the equal superposition. A phase gate rotates the qubit around the vertical axis without changing the probability of measurement outcomes, but changing the quantum phase in ways that matter for interference with other qubits. An entangling gate creates correlations between two qubits that cannot be described by any two separate points on two separate spheres. They are now a single point in a combined space with 4 poles, not 2. Add a third qubit and the combined space has 8 poles. Each gate operation moves the entire system through this exponentially growing geometric space. The computation is a trajectory through a space of 9 quadrillion dimensions. The answer emerges from where that trajectory ends, and the trajectory is only possible because superposition is physically real at every point along it. When you don't know where your keys are, they still have a location. They are in one specific place, and your ignorance doesn't change that fact. The keys exist somewhere definite, you just don't know where. This is how most people intuitively understand quantum uncertainty. There's a real answer, you just can't see it yet. The quantum world is like a coin in your pocket. You don't know if it's heads or tails, but it is one of them. Looking at it just reveals what was already true. This intuition is wrong, and understanding why it's wrong is the most important step in understanding what quantum computers are actually doing. The experiment that proves it is over 100 years old has been repeated in dozens of variations with increasing precision and has never once produced a result consistent with the coin in a pocket picture. Fire a single electron at a barrier with 2 small slits in it. On the other side, place a detector screen. If the electron behaves like a particle, a tiny billiard ball with a definite position at every moment, it will pass through one slit or the other and leave a single mark on the screen behind whichever slit it chose. Over many trials, you would get 2 clusters of marks. This is the classical prediction. It matches how pebbles behave. It is not what happens. What happens is an interference pattern. Alternating bands of high and low impact density spread across the screen, the same pattern you would get if you sent a water wave through 2 slits instead of a particle, which means the electron, a single electron with no other electrons around it, is going through both slits simultaneously. It interferes with itself. The wave pattern is produced by one particle taking both parts at once, and those parts overlapping on the far side. Close one of the slits. The interference pattern disappears. Open the second slit, and it returns. The electron behaves differently depending on what paths are available, even before it reaches the barrier. Set up a detector at the slits to find out which one the electron goes through, and the interference pattern disappears again. The act of gaining information about the electron changes what the electron physically does. Delayed choice experiments proposed by John Wheeler and then run in the laboratory showed you could decide whether to measure which slit after the electron had already passed through the barrier. The electron's past behavior changed depending on a future measurement decision. The electron responds not to the measurement device, but to the information the measurement device would create. Here is where the proof anchors matter. Because this is not philosophy, it is measurement. In 1971, physicists Joseph Hafler and Richard Keating flew cesium atomic clocks on commercial airliners around the world in both directions and compared them to clocks left on the ground. The flying clocks ran at different rates than the ground clocks, not approximately, measurably. This is quantum behavior made legible in hardware. In 2023, the GPS satellites orbiting Earth require their atomic clocks to be corrected by exactly 38 microseconds per day to account for the quantum effects of relativity. Without that correction, GPS would accumulate errors of roughly 11 kilometers per day. Your phone navigates because quantum mechanics is real enough to build error corrections around. We have done this experiment many times. The result is always the same. The wave function is what physicists use to describe the electron before that measurement. It is a mathematical object that assigns a probability amplitude to every possible state the electron could be in. But the wave function does not describe a particle whose properties exist but are hidden from you. Under the standard interpretation of quantum mechanics, the wave function is the most complete description of reality that exists. The electron does not have a definite position that you simply happen not to know. It has no definite position. The position is genuinely undefined until measurement forces it to take one. Here is the concrete consequence of this for the double-slit experiment. If the electron had a definite position at every moment, then in principle you could track it. A good enough tracking system would show you which slit it went through, and if you knew which slit it went through, the interference pattern would disappear, not because the tracking system disturbed the electron, but because the electron, if it had a definite position, could only go through one slit, and going through one slit cannot produce an interference pattern. The interference pattern is only possible if the electron goes through both slits, but going through both slits simultaneously requires the electron to have no definite position. It requires the electron to be in a superposition of going through the left slit and going through the right slit at the same time. The interference pattern is direct observational evidence that the electron is in superposition, and the fact that installing a detector eliminates the interference pattern is direct observational evidence that gaining information about the electron's position forces it to choose a slit, which forces it to have a definite position, which destroys the superposition. Measurement creates definiteness. Definiteness destroys superposition. Superposition is real. The difference between unknown and undefined is not a semantic nicety. Unknown means reality has an answer, and you lack access to it. Undefined means reality does not have an answer yet. The electron is not hiding. It is not in one place while appearing to be in two. It is actually, physically, in no particular place at all until something interacts with it and forces a definite outcome to emerge. The definiteness is not revealed by measurement. It is produced by measurement. Sit with that for a moment. Einstein spent the last 30 years of his life convinced this was wrong. In 1935, he co-wrote a paper with Boris Podolsky and Nathan Rosen, arguing that the wave function must be incomplete. Particles must have what he called hidden variables, definite properties that exist whether or not anyone measures them. The apparent indefiniteness, Einstein argued, is an artifact of our ignorance, not a feature of reality. This view, that reality has definite facts and quantum mechanics is just ignorant of them, is the most natural position any reasonable person would take. It is also, as subsequent experiments proved, incorrect. In 1964, John Bell proved that you could test whether local hidden variables exist by measuring correlations between entangled particles from many different angles. If the particles had pre-existing definite properties, their measurement statistics must satisfy a specific mathematical bound. Quantum mechanics predicts violations of that bound. Alan Aspect's 1982 experiment in Paris confirmed violations precisely as quantum mechanics predicted. Anton Zeilinger's group refined the experiments through the 1990s and 2000s, closing the loopholes. The 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Zeilinger for this work. Their experiments demonstrated that particles do not have definite hidden properties before measurement, that the apparent indefiniteness of quantum states is a real feature of physical reality. Einstein was wrong. The definiteness is not hidden. It is produced. The EPR paper was not just a philosophical complaint. It was a technical argument. Einstein, Podolsky, and Rosen constructed a specific scenario involving two particles that had interacted and then separated. They showed that measuring the position of one particle precisely would instantly determine the momentum of the other, regardless of the distance between them. Since measuring position and momentum simultaneously is forbidden by Heisenberg's uncertainty principle, Einstein argued that the second particle must have had definite position and momentum all along. The wave function, by failing to capture these pre-existing definite values, was therefore incomplete. Bell's theorem turned this into an experiment. Bell showed that if particles have pre-existing definite properties, The correlations between their measurements must satisfy a specific mathematical bound. Quantum mechanics predicts correlations that violate this bound. The experiments ran. Quantum mechanics won every time. What makes the Bell inequality violation so powerful as evidence is that it is not just a single experiment. It is a class of experiments repeated hundreds of times in dozens of countries by dozens of independent groups, with improving precision and closing loopholes. The 2015 loophole-free Bell test in Delft, Netherlands, closed the last major loopholes simultaneously. The result was unambiguous. Local hidden variables cannot exist. Quantum mechanics is telling the truth. The indefiniteness is real. And every qubit in every quantum processor is a device that relies on that indefiniteness being real to perform its function. There is an important distinction between what Bell's theorem rules out and what it leaves open. It rules out local hidden variables, meaning it rules out the existence of pre-existing definite properties that are carried by each particle independently and influence only nearby events. It does not rule out non-local hidden variables, meaning hidden variables that are instantaneously connected across space. Pilot wave theory is exactly such a theory, and it is consistent with Bell's theorem. What Bell's theorem rules out is the combination of locality and definiteness. If you want definiteness, you must accept non-locality. If you want locality, you must accept indefiniteness. You cannot have both. This is not a philosophical claim. It is a mathematical theorem with experimental confirmation. And it means that any interpretation of quantum mechanics that is correct must either abandon the idea that events are locally determined, or abandon the idea that events have definite outcomes before they are observed. There is no escape from at least one of these conclusions. And now, in quantum processors cooled to 15 millikelvin, qubits sit in superposition, in the state that has no classical equivalent, waiting for the measurement that will make them definite. They are not hiding their true state. They do not have one yet. That is the physics. That is the world. And the computers are running on it. The entanglement aspect deserves its own attention here, because it is what makes the Bell test results so difficult to explain away. When two particles are entangled, they share a single quantum state. When you measure one of them and get a result, the other particle's quantum state changes instantaneously, regardless of the distance between them. This is not communication. No information travels between the particles, but the correlation between their measurement outcomes is stronger than any correlation that could exist if the particles had pre-existing definite properties. This is what Bell's theorem established. There is a precise mathematical bound on how correlated two systems with pre-existing definite properties can be. Entangled quantum systems violate this bound. They are more correlated than any classically prepared system could be. And this excess correlation is not an artifact of the experiment. It is a property of quantum mechanics. It is what quantum computers exploit. The entanglement between qubits allows the quantum processor to perform correlations that no classical machine can replicate, because no classical machine is operating in a space with 9 quadrillion dimensions, where all those dimensions are simultaneously real. For most of the 20th century, physicists had a practical answer to the problem of quantum indefiniteness at the everyday scale. It was called decoherence, and for a long time it seemed like exactly enough. The idea was straightforward and compelling. Quantum superposition is fragile. An isolated quantum system can maintain superposition because nothing is interacting with it. But in the real world, objects interact with their environment constantly. Photons bounce off them, air molecules collide with them, electromagnetic fields nudge them, and each of these interactions is a quantum measurement of sorts, an exchange of energy and information that forces the quantum system toward a more definite state. Decoherence is the process by which this environmental interaction destroys superposition. It happens extraordinarily fast. For a large object, something the size of a dust grain floating in air at room temperature, decoherence happens on timescales so short they make a nanosecond look like a geological error. The environment effectively measures the object's state billions of times per second. The superposition never has a chance to manifest at the macroscopic scale because it is destroyed before it can become apparent. This is why you don't see chairs in two places simultaneously. The chair is interacting with too many things, too fast for any macroscopic superposition to survive even for an instant. This explanation felt satisfying for decades. It provided a clean, intuitive boundary between the quantum and classical worlds. Down at the scale of individual particles, superposition rules. Up at the scale of everyday objects, decoherence destroys the superposition before it matters. The weirdness stays small. The world stays normal. The boundary is sharp enough to be comfortable. The time scale over which decoherence occurs depends on the environment. For a grain of dust in air at room temperature, it is approximately 10 to the negative 36 seconds. For a single atom carefully trapped in a vacuum chamber and cooled with lasers, coherence can be maintained for seconds or even minutes. For a superconducting qubit in a dilution refrigerator, coherence times of tens to hundreds of microseconds are achievable, which is long enough to run thousands of quantum gate operations before the superposition degrades. The boundary between quantum and classical is not a wall written into the fundamental laws. It is an engineering challenge. Push the environment away far enough, cool the system deeply enough, and quantum behavior persists at scales that would not have seemed possible to earlier generations of physicists. IBM's 433-qubit Osprey processor, announced in 2022, maintained quantum coherence across a system nearly 8 times larger than the Sycamore chip. 8 times more qubits. 8 times more physical objects in genuine quantum superposition simultaneously. In 2023, IBM ran what they called utility scale experiments on 127 qubits, demonstrating that quantum behavior could be maintained and exploited in systems large enough to simulate physically interesting problems in condensed matter physics. The qubits were entangled. The superpositions held. The computations produced results that classical simulations of equivalent accuracy could not replicate efficiently. In late 2024, Google's Willow processor demonstrated quantum error correction below the threshold required for fault-tolerant computing, showing that adding more physical qubits per logical qubit reduces error rates rather than increasing them, which only works if the underlying quantum coherence is real and maintainable at scale. Each of these milestones pushed the scale at which genuine quantum behavior is demonstrated into territory that previous generations of physicists would have assumed was thoroughly dominated by decoherence. Here is the deeper issue. Decoherence explains why you don't see superposition in large objects. It does not explain what happens during measurement. When a quantum system decoheres, it becomes entangled with its environment. The superposition doesn't disappear. It spreads. The environment becomes part of the quantum state. The whole system, particle plus environment, is now in a superposition. Just a superposition so large and so tangled with so many particles that no measurement device you can build could detect the interference between the branches. The interference becomes practically undetectable. It does not become zero. Decoherence hides the superposition. It doesn't end it. And that distinction between hidden and ended is exactly where the measurement problem lives and exactly what quantum computers are keeping experimentally alive. There is a moment in the decoherence story that physicists sometimes skip past too quickly, and it's the moment where the real strangeness lives. When a quantum system decoheres, the standard description says its superposition is destroyed by interaction with the environment. But what the mathematics says is that the quantum system and the environment become entangled with each other. The superposition does not disappear. It spreads into a larger system. The wave function of the combined system is still quantum. It still describes a superposition, but it is a superposition of a system with so many particles that the interference between its branches becomes undetectable by any measurement you could ever make. Environmental interaction selects certain states of the quantum system as preferred, the states that are least disturbed by interaction with the environment. These are called pointer states, the states that correspond to the classical properties we observe. Position is a pointer state for large objects. The environment continuously measures position through the random bombardment of photons and air molecules, and any quantum superposition of different positions collapses rapidly into one of the pointer states. Classicality, in this picture, is the set of states that the environment prefers. It is not fundamental, it is selected. What quantum computers demonstrate is that by carefully controlling the environment, you can control which states the environment selects. In a quantum processor, the engineering prevents the environment from selecting any pointer states at all. The qubits are isolated from the thermal, electromagnetic, and mechanical environment. The only interactions they have are the deliberately applied quantum gates, and in this controlled environment, the qubits remain quantum. The boundary between quantum and classical is not a property of the system. It is a property of the environment the system is in. This reframes what quantum computing engineers are doing at a conceptual level. They are not just building faster computers. They are creating islands of quantum reality in a classical world. Every dilution refrigerator is a machine designed to prevent classicality from intruding. Every layer of electromagnetic shielding is a wall against the environmental measurements that would force the qubits to become definite. Every microsecond of coherence time is a measurement of how long quantum reality can be sustained against the pressure of a classical environment. The engineers are not fighting entropy exactly. They are fighting information flow. They are preventing the outside world from learning what the qubits are doing. And in that prevention, in that enforced ignorance, the quantum computation runs. The timescale of coherence is itself a kind of data about reality. IBM's Heron processor, announced in late 2023, achieved error rates per 2-qubit gate that were several times lower than its predecessors. The improvement came from better isolation and better gate design. Better isolation means the environment is learning about the qubits more slowly. Lower error rates mean the superposition is being disturbed less often. Every engineering improvement in quantum computing is simultaneously a scientific measurement of how thoroughly the environment can be excluded and how long the quantum state can be maintained when it is. The machines are probes of their own operating conditions, and those conditions are the conditions under which the quantum classical boundary lives. The pattern in the data is consistent and clear. Each year the processes grow larger. Each year the coherence times improve. Each year the results demonstrate quantum behavior at scales that the previous year's models predicted would be dominated by decoherence. The threshold at which quantum mechanics gives way to classical behavior keeps retreating, not disappearing, not being disproved, just retreating. The line holds further out than the models expected, and the question physicists are now asking, quietly and seriously, is whether the line exists where they thought it did at all. What quantum computers demonstrate is that the boundary between quantum and classical is not fixed by the physics. It is fixed by the engineering, and the engineering keeps improving. This has consequences for the measurement problem that go beyond what philosophers argued about in 1927. If the boundary is an engineering parameter rather than a physics parameter, then the question of where the quantum classical boundary actually lies is an experimental question, not a philosophical one. It can be measured, it can be probed, it can be pushed, and every year the engineering pushes it further. The answer to what reality is at the boundary becomes more urgent and more accessible. The machines are not just demonstrating superposition, they are mapping the terrain where quantum meets classical, 1 qubit at a time. The measurement problem is this. Quantum mechanics describes a system evolving smoothly and deterministically according to the Schrödinger equation, a wave that spreads and develops and follows precise mathematical rules with no randomness at all. Every quantum system obeys this equation without exception. The equation is linear, which means superpositions remain superpositions. They don't spontaneously collapse. They evolve, interact, entangle, grow more complex, but they stay quantum. The equation has no mechanism for producing a single definite outcome. It produces a superposition of all outcomes, each weighted by its probability amplitude. It describes everything except the one thing that experiments actually observe, a single result. But when you measure a quantum system, you don't get a superposition. You get one outcome. The electron lands here. The qubit reads 0 or 1. The measurement result is definite, singular, classical. The superposition, which the wave equation says should still be there, is gone. Something happens at the moment of measurement that the wave equation doesn't describe. Exactly what happens is what no one has agreed on since 1927. A century in. Still open. The standard textbook answer is that the wave function collapses. Before measurement, the particle is in a superposition. At measurement, the wave function collapses to a single outcome. with the probability of each outcome given by the Born rule, which says you square the absolute value of the probability amplitude. This is not a derivation from the Schrödinger equation. It is an additional postulate added to quantum mechanics to explain why measurements produce definite results. The collapse is not described by any equation in the theory. It is added separately by hand as a rule that applies when measurement occurs. The theory has two modes: smooth deterministic evolution and abrupt probabilistic collapse. The theory does not say what a measurement is, or what physical process constitutes collapse, or exactly when it occurs. Erwin Schrödinger understood the problem immediately. In 1935, he proposed a thought experiment designed to expose the absurdity. Place a cat in a sealed box with a radioactive atom. If the atom decays, a mechanism releases a poison that kills the cat. If not, the cat lives. Wait 1 hour. Quantum mechanics says the atom is in a superposition of decayed and not decayed. The decay detector is entangled with the atom. The poison mechanism is entangled with the detector. The cat is entangled with the mechanism. So according to the wave equation, the cat is in a superposition of alive and dead until you open the box. Schrödinger was not proposing a cute puzzle. He was demonstrating what happens when you take the wave equations seriously, all the way up to macroscopic scales. The world has no definite facts until someone looks. He died in 1961 without a satisfactory answer. The question is still open. The interesting thing about the Schrödinger cat scenario is not that it is absurd, it is that it is correct quantum mechanics. If you actually seal the cat in a box with a quantum decay detector and waited, the wave function of the combined system would indeed describe a superposition of the alive and dead states. The cat would be in superposition according to the Schrödinger equation. The reason we don't consider this a serious practical problem is decoherence. The cat is enormously coupled to its environment. The air in the box, the photons bouncing around inside it, the thermal vibrations of every molecule, all of these are continuously measuring the cat and measuring the mechanism and measuring the vial of poison. The superposition is destroyed almost instantly. The cat is classical in practice because the environment will not allow it to remain quantum even for a nanosecond. But Schrödinger's point was not about whether the superposition persists, it was about what the wave equation says is happening. And what the wave equation says is happening before any of those environmental measurements destroy the superposition is a superposition of alive and dead. The wave equation does not recognize the difference between a cat and an electron. It applies the same laws to both. The difference in behavior comes entirely from the environment, not from the physics. The measurement problem is also not resolved by appealing to the fact that quantum mechanics works. Of course it works. Working is not the same as being understood. Classical electrodynamics worked for 50 years before physicists understood its connection to relativity. Newtonian gravity worked for 2 centuries before Einstein showed it was an approximation of a deeper theory. A theory can be spectacularly successful at predicting outcomes while remaining genuinely silent about what is happening physically. Quantum mechanics is that theory. It predicts everything. It explains in the sense of providing a mechanism, nothing. The measurement problem is the gap where the mechanism should be. What makes this particularly hard to hold in mind is that the missing mechanism is not missing in an obscure way. It is missing right at the center of the theory. Every time any quantum system is measured, anywhere in the universe, the wave function collapse happens or something equivalent to it happens. It is not a rare event. It is the most common event in physics. Every photon hitting every surface. Every atom colliding with its neighbors. Every interaction that produces a definite outcome from a quantum state is an instance of the measurement problem playing out. The problem is not confined to laboratories. It is everywhere, always, and the theory that describes it most precisely does not say what it is. Every interpretation of quantum mechanics that reproduces the experimental predictions correctly requires you to accept something about reality that has no precedent in human experience. This is not a sign that physicists are confused. It is a sign that reality is genuinely strange at a level our intuitions were not built to handle. The mathematics is telling the truth. Our picture of the world has to change. The question is which change? The Copenhagen interpretation says the wave function is a tool for predicting measurement outcomes, not a description of what physically exists between measurements. Before measurement, quantum systems don't have definite properties. The question, what is the electron doing before measurement, is not a question physics can answer, because physics only describes what happens when systems interact with measuring devices. Don't ask what reality is, ask what reality is, ask what results measurements produce. This is operationally sufficient. It is what most physicists use when they calculate, but it divides the world into two kinds of things, quantum systems and classical measuring devices, without saying where the boundary is or what physical property marks it. Measuring devices are made of atoms. Atoms obey quantum mechanics. The boundary Copenhagen requires cannot be located in the physics Copenhagen uses. Let that settle before we go further. The Copenhagen interpretation has been the working framework of experimental physics for nearly a century, and its success at producing correct predictions is total. Every experiment that has ever been run is consistent with Copenhagen. Every number that Copenhagen predicts has been confirmed. The interpretation does not fail at predicting. It fails at explaining. It fails at telling you what the prediction is. A prediction of. It succeeds at calculating outcomes, and remains deliberately silent about what those outcomes are. This is sometimes presented as a virtue, a kind of epistemic humility, a refusal to speculate beyond what the evidence can confirm. It is also, depending on how you look at it, a refusal to answer the question that the evidence most urgently raises. The question is, if quantum systems don't have definite properties before measurement, and classical measuring devices do, and measuring devices are made of quantum systems, then where exactly does the definiteness come from? Copenhagen says, from measurement, and when asked what measurement is, physically what process produces the transition from quantum indefiniteness to classical definiteness, Copenhagen says that is not a question physics can answer. Whether this is profound or evasive depends entirely on whether you think the question deserves an answer. The many worlds interpretation refuses the division entirely. It says the wave function never collapses. The Schrödinger equation describes everything, always. When you measure a quantum system and get one outcome, the other outcomes did not disappear. They continue to exist in other branches of the wave function. You, the observer, became entangled with one branch, which is why you experience one outcome. But all branches are equally real. The cat is alive in one branch and dead in another. You open the box in one branch and find it alive, while another version of you, in another equally real branch, finds it dead. The world constantly branches. Every quantum event multiplies reality. Many worlds is mathematically clean. It requires no additional postulate about collapse. The cost is an infinite proliferation of parallel realities so vast that the observable universe is not even a grain of sand in it. The pilot wave theory, formulated by David Bohm in 1952, takes Einstein's side. It says particles do have definite positions and momenta at all times. Hidden variables exist, but the variables are not local. Every particle is guided by a real physical wave that extends through all of space simultaneously. The wave obeys the Schrödinger equation. The particle obeys the wave. The particle only goes through one slit in the double-slit experiment, but the wave goes through both, and the particle's trajectory is shaped by the interference pattern in the wave on the far side. No superposition of the particle, no indefiniteness, just a wave you cannot detect directly, guiding particles whose positions are always definite. The cost is non-locality built into the foundations of physical fields spanning the universe, updating instantaneously across any distance, permanently hidden from direct observation. Relational quantum mechanics, proposed by Carlo Rovelli in 1996, says quantum states are not properties of systems, but descriptions of relationships between systems. When you say an electron has spin-up, that statement is only meaningful relative to a specific observer or measuring device. A different observer might assign a different state to the same electron. Both are equally valid. There is no observer-independent quantum state. Reality is made of interactions and correlations, with no absolute substrate underneath. The physical world is not made of things with definite properties. It is made of relationships. Properties are the interactions. There is nothing underneath the interactions to anchor them. Every one of these interpretations works. Every one of them predicts what quantum mechanics predicts. Every one of them asks you to accept something that would have seemed not merely strange but incoherent to any physicist before 1900. And the quantum computing results are not settling the debate. They are sharpening it, because they are showing that whatever is happening inside a 127-qubit processor during a computation, it is something the physics of definite classical states cannot produce. The definiteness is not the input, it is the output. Something is producing it. What that something is, and what reality looks like before it does, is the question that has been open since the beginning. The Born rule is worth dwelling on because it sits at the center of the measurement problem in a way that is often understated. The Born rule tells you that if a quantum system is in a superposition of states, the probability of getting any particular outcome when you measure it is the square of the absolute value of the probability amplitude for that outcome. This rule is spectacularly successful. It predicts measurement statistics with precision that exceeds 12 decimal places in some cases. It is one of the most precisely confirmed quantitative laws in the history of science, and yet the Born rule is not derived from the Schrödinger equation. It is added as an independent postulate. The theory has two modes. The theory does not say what makes one mode switch to the other, and in a machine running on 127 qubits, that switch is happening every time a result comes out. The Wigner's friend problem, which started as a thought experiment in 1961, has since been turned into a laboratory result. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University in Edinburgh performed the first experimental version using pairs of photons and entangled 6-qubit systems. One part of the system acts as the friend, performing a quantum measurement and recording a definite outcome. Another part acts as Wigner, observing the entire system from outside. The Proietti experiment tested a set of inequalities derived by Česlav Bruckner that any consistent single-world theory must satisfy. If there is one objective reality that all observers agree on, those inequalities hold. The experiment violated them. Quantum mechanics predicted the violations. The result means that quantum mechanics is inconsistent with the existence of a single observer-independent account of all events, unless you modify the theory. Not every physicist agrees on how to interpret this result. All of them agree it happened. What this means for the debate between interpretations is not resolution, but sharpening. Every interpretation of quantum mechanics, when applied to the Wigner's friend scenario, produces a story about what is happening. In Copenhagen, there is no single objective story, and that is acceptable because Copenhagen denies that stories between measurements exist. In many worlds, both Wigner and the friend are correct because they are in different branches of the wave function. In relational QM, both descriptions are correct relative to their respective physical systems, and the apparent contradiction dissolves because there is no observer-independent fact to be contradicted. In Cubism, the friend's experience is definite for the friend, and Wigner's superposition is correct for Wigner, because these are different agents' belief states, not claims about an observer-independent world. The experiment does not select between these responses. It eliminates the naive view that there is a single set of facts about quantum events that all observers can agree on, independent of their physical relationship to the events. The world, it turns out, does not have a view from nowhere. The measurement problem has been a philosophical debate for a century. For most of that time, it was possible to treat it as a debate without practical stakes. The mathematical predictions of quantum mechanics match every experiment. The technology built on those predictions works. Whatever interpretation you prefer, the numbers come out the same. Quantum computers change the relationship between the foundations and the laboratory. The 2019 Google Sycamore results was contested immediately. IBM's research team argued that a properly optimized classical supercomputer could replicate the Sycamore result in 2.5 days rather than 10,000 years. Google disputed the numbers. The technical argument was detailed and serious. But something important happened in the middle of it. The argument was not about whether quantum superposition is real. It was about how fast a classical computer can simulate it. Even Google's critics were conceding that simulating a 53-qubit quantum system classically is computationally expensive and becomes exponentially more expensive as the system grows. The disagreement was about exactly when quantum advantage becomes undeniable, not about whether quantum mechanics is doing something classical mechanics cannot. In 2023, IBM published results from their 127-qubit Eagle processor. The team demonstrated quantum utility in simulating the dynamics of a quantum material, the transverse field Ising model, a system of quantum spins interacting in a specific way that appears throughout condensed matter physics. The quantum processor computed the time evolution of this system with accuracy that matched exact classical calculations in the regime where exact calculations are still feasible, and then continued into regimes where exact classical simulation becomes impossible. Not difficult, impossible in any practical sense. For this to be valid, 127 physical qubits must be genuinely entangled in a coherent quantum state through the entire computation. If the qubits were simply in classical states with unknown values, the simulation would fail. It doesn't fail. In late 2022, Google published results demonstrating the creation of a time crystal on their Sycamore processor. A time crystal is a system that oscillates between two states periodically without absorbing energy to sustain the oscillation. Creating one requires many qubits entangled in a state that maintains quantum coherence through many oscillation cycles. Because the oscillation is driven by the quantum dynamics of the entangled system, not by any external energy input. Google created one on a 20-bit system. The superposition held for hundreds of oscillation cycles. Decoherence did not win on the timescale needed. The time crystal persisted exactly as the quantum theory predicted. The 2024 Willow results from Google demonstrated quantum error correction below the threshold required for fault-tolerant computing for the first time. Quantum error correction works on redundancy, one logical qubit encoded into many physical qubits, with errors on individual physical qubits detected and corrected without destroying the logical qubit's quantum state. This requires the quantum correlations between physical qubits to be real and precise enough to encode error information separately from logical information. The Willow results showed error rates for logical qubits decreasing as more physical qubits were added per logical qubit. The error correction worked as predicted. You cannot do quantum error correction without quantum superposition. The fact that it works is the evidence. Each of these experiments is a data point in a pattern. The scale at which quantum behavior persists keeps expanding. Each year, the processes get larger and the coherence times improve. Each year, the results demonstrate quantum behavior at scales that previous models predicted would be dominated by decoherence. The boundary retreats. The question of where it actually is does not have a settled experimental answer, and the trend is that the answer keeps being larger than we thought. If you're following this and it's landing the way I hope it is, hit subscribe if you haven't yet. We're about to go further in. There is a subtlety in the 2023 IBM results that deserves careful attention. The team verified their results in the regime where classical simulation is still possible, and found agreement. The agreement in the testable regime is evidence that the quantum processor is implementing the physics correctly, and the results in the untestable regime are what the correctly implemented physics produces. The quantum processor is not a black box. It is a precisely characterized device whose outputs can be trusted because they match where we can verify them, and then continue where we cannot. The implications of the retreating boundary extend into the foundations of physics. If quantum coherence can be maintained at the scale of thousands of qubits, then the question of where the quantum classical boundary lies becomes not just a philosophical question, but a precision measurement problem. There is presumably a scale, or a set of conditions at which quantum behavior must give way to classical behavior in some absolute sense. Finding that boundary, measuring it, characterizing it, would be one of the most significant experimental achievements in the history of physics. It would tell us something fundamental about the structure of reality, at the boundary between what the world is and what we experience the world to be. Every qubit added to a quantum processor is a probe of that boundary. Objective collapse theories attempt to locate this boundary by adding a physical mechanism for wave function collapse to quantum mechanics. GRIW theory, proposed by Girardi, Rimini, and Weber, adds a spontaneous collapse mechanism. Particles randomly collapse their wave functions at a fixed rate, independent of measurement. The rate is chosen to be negligible for single particles, but rapid enough to collapse macroscopic objects nearly instantaneously. GRW predicts subtle deviations from standard quantum mechanics at intermediate scales, deviations that would be measurable in sufficiently precise experiments. No such deviations have been found. The theory is alive. It is not confirmed. The measurement problem remains open. But the search for deviations is ongoing, and quantum processors provide a new testing ground. If spontaneous collapse occurs at some scale, quantum computers operating above that scale would fail in specific, predictable ways. They have not failed in those ways. Every successful error correction cycle, every successful computation above a certain qubit threshold is a negative result for objective collapse theories. The machines are not just doing computation, they are doing physics. The Penrose-Diossi model, developed independently by physicists Roger Penrose and Leos Diossi, proposes that the wave function collapses when the gravitational difference between two superposed mass configurations reaches a certain threshold. More massive objects collapse faster because the gravitational difference between their two superposed positions is larger. For a small particle, the threshold is almost never reached, which is why particles maintain superposition. For a large object, the threshold is reached almost immediately, which is why large objects appear classical. This is a specific, testable prediction. If the Penrose-Diossi model is correct, quantum superposition should break down at a mass scale that can be calculated. Experiments probing quantum behavior in heavier and heavier objects are underway. So far, quantum behavior persists further up the mass scale than simple versions of the model predict. The model is not ruled out, but it is being squeezed. And quantum computers, by maintaining quantum coherence in systems of increasing scale, are among the tools doing the squeezing. Every interpretation of quantum mechanics was developed before quantum computers existed as functioning devices. Copenhagen was fully articulated by 1927. Many worlds was proposed in 1957. Pilot wave was formalized in 1952. Relational QM came in 1996. These were philosophical positions about mathematical structure, developed when the largest quantum systems anyone could deliberately control contained a handful of particles. The interpretations were not predictions about quantum computers. They were frameworks for making sense of quantum mechanics before quantum mechanics became an engineering discipline. Quantum computers are now constraining these frameworks in ways their originators could not have anticipated, not by ruling any of them out, since all interpretations predict identical measurement outcomes, but by making the question of what happens inside a coherent quantum system experimentally concrete in a way that was not previously possible. When the quantum system is 127 qubits running a computation that produces verifiable results, the question what is the system doing between measurements is no longer just philosophical. It is a question about the substrate of a calculation that produces numbers. Take Copenhagen. Its central move is to say that quantum mechanics is a tool for predicting measurement outcomes, not a description of what exists between measurements. This was defensible when quantum systems were individual particles. It becomes harder when the system is a 433-qubit processor running a material simulation for microseconds before any classical readout occurs. At what point in the computation does the measurement happen? The processor runs through thousands of gate operations. It maintains quantum coherence through all of them. Something is happening physically during all of those operations. Something is changing. Something is computing. Copenhagen's answer, that the question doesn't have a physically meaningful answer before measurement, feels less like a solution and more like a declaration that the question is not allowed. Many worlds handles the quantum computing results differently, and, some physicists argue, more naturally. In many worlds, the processor's qubits are in genuine superposition. All outcomes of each gate operation occur in all branches simultaneously. The computation extracts a result by allowing the branches to interfere before readout, amplifying the correct answer and suppressing the wrong ones across branches. David Deutsch, who invented quantum algorithms in his 1985 paper, has argued explicitly that quantum computing is practically evidence for many worlds. The argument is direct. A quantum computer performs computations that no classical computer could match. If it is not the parallelism of many branches doing the work simultaneously, Where is the work being done? Deutsch's answer is that the branches are real and the speed-up is their signature. The counterargument to many worlds is the probability problem. In many worlds, every outcome of every quantum measurement occurs in some branch. But quantum mechanics assigns different probabilities to different outcomes through the Born rule. In many worlds, they all happen. So what does it mean to say one outcome is more probable than another if you are guaranteed to exist in a branch where each outcome occurs? Deriving the Born rule from the Schrödinger equation alone, within a many worlds framework, requires additional assumptions about what it means to be an observer in a branching universe. Those derivations exist. They are contested. The problem has not been dissolved. Cubism, quantum Bayesianism, developed by Christopher Fuchs and Rüdiger Scheck, says the wave function is not a description of the world. It is an agent's belief state, a compact encoding of an individual's expectations about the outcomes of future measurements. When an agent measures a quantum system and gets an outcome, they update their wave function the way a Bayesian reasoner updates probabilities on new evidence. The wave function was never a physical thing. It was always a representation of personal expectations. There is no wave function of the universe, because the universe has no agent relative to which that wave function is defined. The challenge Cubism faces from quantum computing is consistency. When a quantum processor computes a result verified by many independent researchers in independent laboratories, the agreement suggests something outside any individual agent's belief state is being tracked. Cubism's response is that the consistency is the expected result of agents who have interacted with the same physical systems following the same norms of rational belief updating. The world is real. The wave function is not a property of the world. The pilot wave interpretation handles the quantum computing results through a picture that is in some ways more intuitive than many worlds. In pilot wave, every qubit has a definite state at every moment. The state is hidden, guided by the pilot wave. But it is there. The computation works because the pilot wave evolves through all possible computational paths simultaneously, and the physical qubit state follows the path that the pilot wave guides it to. The computation is done by the wave. The result is read from the particle. This picture is deterministic. The cost is a physical field spanning all of space, updating instantaneously across any distance, permanently hidden from direct observation. None of these interpretations predicts outcomes that don't occur. The debate is not between theories with different experimental predictions, it is between theories that all predict the same things but require different pictures of what reality is doing when no one is measuring it, and the quantum computing results have not broken the tie. What they have done is demonstrated that some revision to the classical picture of reality is necessary, because something genuinely quantum is happening in those machines. And whatever it is not classical, and it is not ignorance. The situation the interpretations leave you in is precise. Every interpretation of quantum mechanics that has been proposed is self-consistent. Every interpretation makes the same predictions, and every interpretation requires you to accept something that violates at least one deeply held intuition about what the world is like. Copenhagen violates the intuition that reality exists independently of observation. Many worlds violates the intuition that there is only one world. Pilot wave violates the intuition that physics is local. Relational QM violates the intuition that reality is absolute. Cubism violates the intuition that physics describes something beyond human agents. These violations are not small. They are not edge cases. They are structural features of what the theory requires if you want it to be consistent all the way down. And the quantum computing results, by demonstrating genuine quantum behavior at scales and in contexts that have no historical precedent in the laboratory, make the question of which violation you can accept more urgent than it has ever been. David Deutsch made the case in his 1997 book, The Fabric of Reality, that quantum computing provides direct empirical support for the many worlds interpretation, not just philosophical preference. His argument is simple. The computation being done by a 53-qubit quantum processor cannot be done by a single classical universe. The state space is too large. The computation is too fast. If you take quantum mechanics seriously as a description of reality, the computation must be happening somewhere. Many worlds says it is happening in parallel branches, all of which are real. Copenhagen says the question of where it is happening is not a meaningful physical question. Pilot Wave says it is being done by the pilot wave, which spans all of space. Relational QM says it is a description relative to the measuring device, not an absolute computation in any objective universe. Each answer is different. Each is consistent with the experimental results, and the fact that we cannot choose between them on the basis of any experiment that has ever been run is not a temporary gap in knowledge. It is the current state of foundational physics. There is a version of the quantum measurement problem that appeals to people who find it simultaneously disturbing and secretly flattering. It goes like this. The wave function collapses when it is observed. Observation reclapses a mind. Therefore consciousness causes collapse. Reality is brought into being by awareness. The universe needs observers to exist. This version has appeared in popular books, in films, in spiritual frameworks that reach for physics to support conclusions about the primacy of mind. This version is wrong, and the reasons why it is wrong bring you closer to what is actually strange about measurement than the appealing version does. The intuition makes sense in evolutionary terms. Our brains evolved in a world where attention and observation are causally connected to outcomes. You look for the predator. You find the predator. The act of looking is useful precisely because it changes what you do next. But the universe does not recognize this category. The universe does not care whether the thing registering information is a human brain, a germanium detector, a photographic plate, or a camera running in an empty room. What matters to the physics is physical information, not awareness. Physical correlation between systems. The first physicist to take the consciousness interpretation seriously in a rigorous way was John von Neumann in his 1932 mathematical formulation of quantum mechanics. Von Neumann showed that from a purely mathematical perspective, you could delay the moment of wave function collapse arbitrarily far up the chain of interactions between the quantum system and any measuring apparatus. The electron interacts with the detector. The detector is made of atoms that obey quantum mechanics. Treat the detector as part of the quantum system. Push the collapse to the amplifier. Push it to the recording device. Push it to the experimenter's retina. Push it to the visual cortex. At each step, the physics has no reason to stop the superposition from spreading. Von Neumann concluded the chain must stop at the boundary between the physical and the mental. The problem was identified almost immediately, and it is fatal. If consciousness collapses wave functions, the size and complexity of the conscious system should matter. A mouse brain should collapse wave functions differently from a human brain. An unconscious brain under anesthesia should not collapse them at all. A camera should never collapse anything. Each of these predictions is testable. None of them correspond to what experiments show. Automated measurement systems with no human in the loop produce the same quantum measurement statistics as measurements observed by fully conscious humans. Cameras left running in empty rooms produce interference or collapse, depending on whether they carry information about which path was taken, not on whether anyone is watching. Consciousness is not the relevant variable. What is the relevant variable is physical information. A measurement in quantum mechanics is any interaction that creates a physical record of a quantum system state. The detector clicking, the photographic film being exposed, the magnetic state of a memory cell being altered. An entanglement being established between the quantum system and another physical system in a way that correlates their states irreversibly. These are physical events. They do not require awareness. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University in Edinburgh performed the first real laboratory version of the Wigner's friend scenario. Eugene Wigner had proposed the thought experiment in 1961. A physicist's The Friend performs a quantum measurement inside a sealed laboratory and records a definite outcome. From the Friend's perspective, the wave function has collapsed. But Wigner, standing outside the sealed lab, has no information about what happened inside. From Wigner's perspective, the entire laboratory, including the Friend and the measurement result, is still in a quantum superposition of all possible outcomes. The Proietti experiment used pairs of photons and entangled 6-qubit systems to create an analog of this scenario, and tested inequalities derived by Kaslev-Bruckner that any consistent single-world theory must satisfy. The experiment violated them. Quantum mechanics predicted the violations. The result means that quantum mechanics is inconsistent with the existence of a single observer-independent description of events that all observers agree on. What this means for the concept of observation is precise. You, the person reading these words, do not have a special relationship to the quantum wave function that a well-designed thermometer does not also have. Both of you establish physical correlations with the systems you interact with. Both of those correlations count as measurements. Which means the measurement problem is not a problem that arises in special laboratory conditions. It is the physics of every interaction that has ever occurred. Every photon hitting every surface, every particle colliding with every other particle, every atom in your body interacting with its neighbors. All of it is measurement. All of it is the process by which correlations form, by which the definite emerges from the quantum, by which the world acquires the classical appearance it has. The question of what the world is before that process occurs is a question about every moment and every place. The practical consequence is that the observer role in quantum computing is precisely defined and not mystical. The observer is the measurement apparatus at the end of the computation. The moment of observation is the moment of readout, when the classical electronics record the final state of the qubits. Before that moment, the computation is running in a quantum state that is definite relative to nothing outside the quantum system. After that moment, the result is definite relative to the measurement apparatus and therefore relative to everything the measurement apparatus is correlated with, which includes the experimenters and eventually, through the spread of information, the rest of the world. Observation is physical correlation. It is not awareness. It is not attention. This has a specific and important implication for how you understand your own position in relation to the quantum world. When you observe the output of a quantum computation, you are not the thing that made the result real. The result was made real by the measurement apparatus at the end of the circuit. By the time you read the number on the screen, the wave function collapsed microseconds ago, in silicon, mediated by classical electronics that have no more awareness than a thermometer. Your reading of the number is just another physical correlation in a chain of physical correlations that began with the qubit and ended with the photons hitting your retina. Every step in that chain is equally a measurement in the quantum mechanical sense. Every step is equally devoid of any special property called consciousness. The awareness at the end of the chain does not retroactively explain the correlations along the way. It is simply the last one. There is something clarifying about this picture, even if it is not immediately comforting. It means the quantum world is not waiting for you. It is not suspended in possibility until human attention arrives to make it real. Physical interactions are happening everywhere all the time, establishing correlations, producing definiteness, measuring and being measured. The universe is processing itself continuously and thoroughly without any need for awareness at any step. Consciousness is a late arrival in the history of the universe. An emergent property of physical systems organized in a very specific way, dependent on quantum processes at its foundation, and in no sense responsible for those processes. The universe was establishing correlations and producing definite events for nearly 14 billion years before anything in it developed the capacity to notice. It did not need noticing to proceed. Imagine you are holding a coffee cup. It feels solid. You know where it is. It is not in two places simultaneously. It is not in an indefinite state waiting for measurement to fix its position. The coffee cup is here, in your hand, and the world seems to have no trouble with that fact. You put it down, leave the room, come back, and it is still there. Reality, from the perspective of your experience, is continuous, definite, and independent of whether you are looking at it. Physics agrees that the cup is classical, but it requires much more explanation than the agreement implies. The coffee cup is not in a quantum superposition of positions because it is coupled to an environment of approximately 10 to the 23rd atoms, all of which are constantly interacting with each other and with the air molecules in the room, and with the photons passing through from the light source. Decoherence operates on this system at rates so fast they do not have everyday equivalents. The environment effectively measures the cup's position billions of times per second. Any quantum superposition of the cup's macroscopic position would be destroyed before it could propagate even a single atomic diameter. The cup is classical because the environment measures it continuously, overwhelmingly, and irreversibly. Its classicality is earned through constant interaction. It is not given. It is not fundamental. Remove the environment. Cool the cup to 15 millikelvin. Seal it from every photon and air molecule and vibration. Isolate it as thoroughly as a quantum processor is isolated, and quantum mechanics would apply to the cup the way it applies to the qubits. The cup would exist in superposition. It would be both here and there, to the extent that here and there are even meaningful descriptions of a quantum state that has no definite position at all. The cup's classicality is a consequence of its interaction with the world. It is not a consequence of the cup being large. Large things can, in principle, be quantum. They are classical because the world doesn't give them the option of remaining quantum. Wojciech Surek at Los Alamos National Laboratory developed a framework called quantum Darwinism that provides a physical mechanism for why the world looks classical to observers embedded in it. In quantum Darwinism, the environment doesn't just decohere a quantum system, it records multiple redundant copies of certain properties of the system. The copies are broadcast outward into the environment and become accessible to many observers independently, without those observers disturbing each other's information. The properties that survive this redundant broadcasting are the classical properties. The position of the coffee cup is classical because it is the property that photons bouncing off the cup carry redundantly to many observers simultaneously. Any quantum properties of the cup that cannot survive this broadcasting process are lost into the environment and become effectively inaccessible. Classicality, in this picture, is not fundamental. It is what survives environmental broadcasting. It is the subset of quantum reality that can be shared among many observers without contradiction. Carlo Rovelli's relational quantum mechanics suggests that what quantum mechanics is describing is the structure of physical information, not the structure of physical objects in themselves. A system doesn't have properties in the abstract. It has properties relative to other systems it has physically interacted with. The physical world is not made of things with definite states. It is made of interactions that establish correlations between systems. Reality is relational all the way down, with no observer-independent substrate underneath the relationships. This is the most honest thing the field can currently say. Not that reality doesn't exist. Not that observation creates it from nothing, but that the question what is really there between observations may assume a framework, an observer-independent reality with definite intrinsic properties, that quantum mechanics does not support. The most careful statement of where the field stands can be summarized approximately as follows. Quantum mechanics is correct. It has been tested more thoroughly than any other theory in the history of science. The wave function is real in some sense. The measurement process is a physical process that produces definite outcomes. The mechanism by which definite outcomes emerge from the quantum state is not fully described by the Schrödinger equation alone. The correct description depends on which interpretation you accept. No experiment has yet distinguished between interpretations. The question is expected to remain open for years, possibly decades, possibly longer. What is not open is the underlying fact. Quantum mechanics describes a world in which, before physical interaction establishes a correlation, the properties of physical systems are not definite. They are indefinite in a precise, mathematical, and experimentally confirmed way. The definiteness you experience is produced by physics. It is the output of a process. The quantum is the input. The classical world, every solid surface, every readable instrument, every definite fact about where things are and what they are doing is what quantum mechanics produces when decoherence does its work. Beneath all of it, at the level where the physics lives, the world is not a collection of definite things with definite properties moving through definite positions in space. It is something that becomes definite through interaction, something that exists most fully in relationship, something that looks back at us with a structure our evolved minds were not built to hold without effort. The qubit at 50 millikelvin is in this sense the most honest thing in the modern world. It is not pretending to be classical. It is not approximating classicality. It is not simplified for human comprehension. It is simply in superposition, doing what the physics requires, waiting for the measurement that will make it definite. And in that waiting, it is closer to what the world actually is at the bottom than anything you will encounter in ordinary experience. Your coffee cup is classical, because the world will not let it be otherwise. The qubit is quantum, because the engineers will not let it be otherwise. Both are made of the same physics. Both are governed by the same laws. The difference is the environment, and the environment is everything. What the field is slowly arriving at is a picture in which the question of what is real cannot be answered in the terms we initially brought to it. The terms assume an observer-independent world with definite properties at all times. Quantum mechanics, confirmed by every experiment that has ever been run, describes a world in which that assumption fails at the quantum level and is recovered approximately at the classical level through decoherence and measurement. The recovery is not perfect. It is not observer-independent. It is what physics looks like from inside a world where physical correlations are established through interaction, where classicality is earned rather than given, and where the concept of what is really there depends on what you mean by really. This is uncomfortable. It should be. The discomfort is the physics working as it should. The question of what reality is between observations is also the question of what you are between observations, not in a mystical sense, in the most literal physical sense. The cells in your body are made of atoms. The atoms obey quantum mechanics. The quantum mechanics of your atoms produces the classical behavior of your cells through decoherence, through the overwhelming measurement that each part of you performs on every other part, billions of times per second. Your experience of being a continuous, located, definite thing moving through time is the classical output of quantum processes. You are a sustained, ongoing classical outcome of a physics that is never classical at the bottom. The qubit at 15 millikelvin is in this sense a mirror, not a mystery. What it shows you is not something alien to your experience. It shows you the substrate of your experience, stripped of the decoherence that makes the experience possible. You cannot perceive superposition from inside a classical environment any more than you can hear a frequency above the range of your ears. The limit is not in the physics, it is in the instrument. You are a classical instrument produced by quantum mechanics, operating in a decoherence regime so thorough that the quantum foundation is invisible from where you stand. The qubit is an instrument tuned to a different regime. It is in the superposition you cannot see. It is doing the thing the universe does at the bottom, and when it is measured, when the classical electronics read out its state and a number appears on a screen, it becomes what everything else is, a definite fact about a world that was, a moment ago, not yet definite. You walked in tonight with a filing system, quantum physics in one drawer, everyday life in another. The label on the quantum drawer said something like, interesting, confirmed, important for computers and lasers, does not affect my morning. That label is harder to read now. What quantum computers are showing is not that physics is broken. It is that physics is working exactly as it should. And what it is showing us is a world that behaves differently from what we assumed at a level so deep that the assumptions we didn't know we were making are the ones now being revised. The electron with no position before measurement. The qubit genuinely in two states at once. The 127 qubit processor, maintaining a superposition so large and so controlled that it produces answers a classical world cannot produce. These are not anomalies, they are the world being honest about what it is. The world was always like this. We are only recently building machines that make the honesty undeniable. The honest world does not have an observer-independent fact about what is happening before you interact with it. Not at the particle level, not in the qubit. Not in any system small enough and cold enough and isolated enough to remain quantum. What is there before the measurement is something the mathematics describes carefully, and our language describes badly. A superposition of possibilities that are all real in some sense, and none of which are actual in the sense you usually mean by real. The definiteness you experience is something the world produces for you through the constant, overwhelming measurement that your environment performs on everything you interact with. The definiteness is a service the universe renders to observers embedded in it. It is not a given. It is not free. The coffee cup in your hand is classical. The atoms in the coffee cup are not. The cup is definite because it is measured, continuously and overwhelmingly, by the environment around it, by the photons in the room and the air molecules pressing against it, and the thermal vibrations of its own lattice. Its classicality is earned. Remove the environment, cool it to 15 millikelvin, Isolate it from every photon and vibration, and quantum mechanics would apply to the cup the way it applies to the qubits in that cylinder in Mountain View. The cup would be in superposition. It would be both here and there, the same physics, the same equations, the same world. You are in the same situation as the coffee cup. Your cells are classical because they are constantly measured by everything around them. Your experience of a definite world, this room, this moment, this singular, now that feels like the only now there is real and is produced by quantum mechanics operating in a regime so thoroughly decoyed that the quantum foundation is invisible from inside the experience. You are the output of a process that runs on superposition. The experience of definiteness is the result. The superposition is the substrate. Physicists don't agree on what the superposition is. They agree that it is there. They agree that it produces the definite world. They do not agree on what happens to it during measurement, or whether the other branches are real, or whether reality is relational or absolute or emergent. A century of effort has narrowed the options. It has not settled them. The question is open not because the experiments haven't been run, but because what the experiments show is a structure in which definiteness is not fundamental, in which the classical world we live in is a particular outcome of a deeper process in which what is really there before you look depends on what you mean by really. The fact that this question remains open after a century of serious effort by serious people is not a failure of physics. It is a fact about the world. The world is genuinely hard to look at from the inside. We are embedded in a classical environment so thoroughly that the quantum substrate is invisible from where we stand. We built machines to peer into the quantum regime, and those machines confirmed that the quantum regime is real, that superposition is physical, that entanglement is physical, that the wave function is doing something real, even if we do not know exactly what. But the machines could not resolve the interpretation problem because the interpretation problem is not about measurement outcomes. It is about what the wave function is in between measurement outcomes. And the wave function, by its nature, can only be tested at measurement. What it is between measurements is the question the measurements cannot answer. What they can answer, and have answered, is that whatever is between the measurements is genuinely quantum, not classical with quantum corrections. Not approximately quantum, genuinely, irreducibly, unavoidably quantum. The qubit at 15 millikelvin is not behaving classically in a way that looks quantum to our limited instruments. It is behaving quantum because quantum is what the universe does at that temperature, at that isolation, at that scale. Every classical thing you've ever touched is doing the same thing at its bottom. You are just insulated from it by the decoherence that your environment provides. Without charge, without effort, without your awareness, every moment that you exist. The word horrifying in the title is not about danger. Nothing in tonight's science is a threat to your physical safety. The quantum world is not going to reach up through the decoherence and disrupt your day. The horror, if that is the right word, is epistemological. It is the recognition that the world you navigate, the world that feels so solid and definite and readable, is a surface phenomenon. It is produced, and what produces it, the quantum mechanics running at the bottom, is something that our minds, evolved to navigate the classical surface, were not built to visualize or intuit. We can do the mathematics. We can build the machines. We can confirm the predictions to 12 decimal places. What we cannot do is see it the way we see a rolling ball or a flipped coin. The world is deeper than our ability to picture it. Once you understand what is happening in that cylinder at 15 millikelvin, you cannot look at a quantum computer the same way. You cannot look at a coffee cup the same way. You cannot look at the room around you the same way. The classical surfaces you navigate are the outputs of a process that produces definiteness from something that is not definite. They are real. They are also produced, and the thing that produces them, the quantum process running at the bottom of everything, is genuinely physically and permanently uncertain until something touches it and makes it real. Somewhere right now in a laboratory cooled to 15 millikelvin, a qubit is in superposition. It is in two states simultaneously. No one is looking at it in any sense that matters physically. The measurement has not happened. The correlation has not been established. And whether there is a fact about what state it is in, whether reality has an answer to that question right now, is a question that the most precise and successful scientific theory ever constructed does not resolve. It just tells you that when you look, you will find one answer. And that has always been enough to build the world. Good night.